told you just during the last meeting, we have two types of power series expansion. The first one we have already discussed, and that is your Maclaurin series, and this one would be another type of function, basically similar, but then it uses a different limit for the value of x, and of course another a different value for the approximating function, or a different equation of the approximating function in this case. So for Taylor series, we suppose that we are interested in a polynomial approximation to p of x from the function f of x over an interval centered at x is equal to a. Now remember that for Maclaurin series, we are taking the interval of the function at x is equal to 0 for Maclaurin. For Taylor series, we are evaluating the function at interval x is equal to a. That is for Taylor series. Okay? So similar with your Maclaurin series, p of x has n plus 1 coefficients. And the idea is also to choose the polynomial p of x such that its first n derivatives match the value of the function f of x and its first n derivatives at x is equal to a. Now we are evaluating at x is equal to a. Computations are simplest if the approximating polynomial is expressed in the form shown below. So this will be the approximating function, or the approximating polynomial that we will use if we are going to evaluate or expand a function using Taylor series. So here. So remember, for Maclaurin series, your approximating polynomial is equal to p of x is equal to c sub 0 plus c sub 1 times x plus c sub 2 of x squared, and so on up to c sub n of x raised to n. Now in this case, this is c sub 2. So for Taylor series, we are replacing the value of x. Instead of x, this will become x minus a, for us to have a simpler computations later on. Okay, so same idea. The first n derivatives of p of x are the following. P of a is equal to c sub 0. Now, where did it come from? Now let's try to show the solution for finding the value of p of a. Now, if you will evaluate your approximating function p of x at x is equal to a, we will do that. This will become c sub 0 plus c sub 1 times x. But take note that x is equal to a. This will become a minus a plus c sub 2 times a minus a squared up to c sub n times a minus a raised to n. Now if you will notice, a minus a will become equal to 0. 0 minus 0 times c sub 1 is 0. So same here, this will become 0 and 0, leaving us with p of a is equal to the constant c sub 0. So that is where it came from. Now, what about for the first derivative of the approximating polynomial? First derivative for this one would be p prime of x. The derivative of the constant c sub 0 with respect to x is 0 plus the constant c sub 1 multiplied by the derivative of this function. The derivative of x with respect to x is 1 minus the derivative of a, constant a with respect to x is equal to 0. Then this will be C sub 2. This is a power function, so you bring down the exponent 2, multiply by the base x minus a, then the exponent minus 1. This is raised to 1. C sub 3, this will become, kung itatagtag natin dito yung C sub 3, C sub 3 x minus a raised to 3. Bring down the exponent, similar process, multiply by the base x minus a, and the exponent minus 1, so this will be raised to 2. So for the last expression of your polynomial, this will become n multiplied by x minus a raised to n minus 1. Okay, so if you will evaluate the value of this first derivative at a, p of a in this case, similar, a minus a here is 0. Similar with the last term, a minus a will become 0. 0 divided raised to n will become equal to, will just be equal to 0. And same with this one. Okay, so it will leave us with the value of the constant c sub 1 times 1, and that would be just equal to c sub 1. Okay, so there, shown in the slide, you have your first derivative of the approximating polynomial evaluated at x is equal to a will be equal to c sub 1. Okay, as of b, if you will try to solve for the second derivative evaluated at a, you will have 2 factorial c sub 2, 3 factorial, or the third derivative of the function, and then you will arrive with this pattern. The nth derivative of the function approximating polynomial evaluated at x is equal to a will just be equal to n factorial times the constant sub n. Okay, so this should be f of a is equal to p of a, f prime of a is equal to p prime of a. Next, we're evaluating at x is equal to a for the Taylor series. This is for the evaluation of Maclaurin series. So from our evaluation a while back, we will arrive at these functions or values for the evaluated values of the approximating polynomial and its first n derivatives. You also have your f sub a, f prime of a, up to the nth derivative of the function evaluated at a. Take note that they will become essentially the same in value with your approximating function. So we have your constants here for your approximating function, and in this case, from your approximating polynomial, if you substitute it, you will arrive with the nth Taylor polynomial for f at x is equal to a. This will become our working formula, working polynomial. Okay, so let's try to evaluate. Let's have an example for this one. Last meeting we have an example of the Taylor series, and we solve the value of sine of x. I think that was sine of 15 using Maclaurin series. For this case, let us try to evaluate f of x is equal to sine of x. If x is equal to, say, 15 again, or 10 degrees now. Let's use 10 degrees as the value of x. So let's imagine that you do not have a calculator. You want to know the value of sine of x. Imagine that you are living in the early times and you don't have a calculator as powerful as what we have now to solve for the value of sine of 10 degrees. So for this one, we have your f of x. This is sine of x. Now, what is the first derivative of the function f of x? This will become cosine of x. If you evaluate again the second derivative of the function, this will be negative sine of x. For the fourth derivative, or the third derivative rather, of the function with respect to x, so that would be similar to isolating the negatives here, negative 1, and evaluating the derivative of the remaining function. The derivative of sine of x is cosine of x. You multiply that by negative 1, you arrive with negative cosine of x, and so on and so forth. From our previous example, take note that this is just repeating itself. This is also equal to p of x, right? P prime of x, p double prime of x, and p the triple prime of x. So that those two are the same because we are evaluating it and we are approximating the function by this polynomial of approximation. So essentially, to get the value, we need to equate them. Okay, so from our discussion, we say that p of a is equal to c sub 0, p prime of a is equal to c sub 1, p double prime of a is equal to 2 factorial c sub 2. Let's proceed with your approximating polynomial. We have it as p of x, the first n sum of our approximating function power series will be equal to c sub 0 plus c sub 1 x minus a, or c sub 0 is equal to c sub 2 divided by x minus a squared plus c sub, or let's just arrive with the last term, x minus a. This is raised to n. So for the values of c sub o, this is equal to p of a. We also have c sub 1 equal to p prime of a. C sub 2 is equal to p this one would be c sub 0 is equal to sine of a. Tama ba? Yung c sub 1 is equal to cosine of a times x minus a. Plus the cosine this will become negative, I think. Yeah, negative sine of a multiplied by x minus a squared and so on up to c sub n x minus a over raised to n. So again, if you evaluate this p of a, this will become sine of a plus cosine of a minus a minus sine of a times a minus a squared. It will become 0. It's essentially become 0. Sine of a, because Taylor series has some of its what do you call this, limitations. So kapag hindi pwedeng Taylor series, ginagamit natin yung Maclaurin series in that case. So those are some limitations on this Taylor series. But essentially, yung Taylor series and Maclaurin series, they are basically the same idea. It's just that we are using a different polynomial approximation, and we can also say that Taylor Maclaurin series is a special case of Taylor series. What if we have your function f of x is equal to 1 over x? The first derivative of this function, that would be f prime of x is equal to, take note that this is a constant divided by variable. So we can use the quotient formula for finding the derivative of this function. This will be x multiplied by the derivative of the constant or the numerator, is 0 minus the numerator multiplied by the derivative of your denominator. And the derivative of your denominator with respect to x is equal to 1. Divide this by the denominator raised to 2. So essentially this will become 1 over negative 1 over x squared. Okay? So for the second derivative of the function, this will become equal to the denominator multiplied by the constant, the derivative of the constant. This will become 0 minus your numerator, negative 1, multiplied by the derivative of your denominator. The derivative of your denominator is 2x, and this will become divided by x squared, the quantity is raised to 2. This will become 0. We will have negative times negative is positive, times 2x is 2x over x raised to 4. But x divided by x raised to 4 will just be equal to 2 over x raised to 3. For the third derivative of the function, this will become the denominator x raised to 4 multiplied by the derivative of your numerator, which is, or here, yeah, here pala. Simple na. X raised to 3 rather. Times the derivative of your numerator, this will become 0 minus the numerator times the derivative of your denominator. This will become 3x squared divided by x raised to 3 the quantity raised to 2. So we have here, this will become 0. Negative 2 times 3x squared is negative 6x squared divided by x raised to 6. But this will cancel 4. And you will have negative 6, or we can say that negative 3 times 2 over x raised to 4. You will notice we have a pattern here. This is also similar to 2 times 1. This is similar to 2 times 1. Alternatingly, nagiging positive, negative, positive, and negative. So we can say, pwede natin gawa ng formula. The kth derivative of the function is equal to negative 1. In this case, 0 pa yung derivative, yan. That's the original function. So k is equal to 0. If k is equal to 0, essentially f of x is equal to negative 1. This will become 0 factorial over x raised to 0 plus 1. For the first derivative, second derivative of the function, this is negative 1 raised to 2 factorial divided by x raised to 2 plus 1. So essentially, we have a pattern here. For the kth derivative of the function, this is equal to negative 1 raised to k times k factorial divided by x raised to k plus 1. So if you will evaluate and look for the value, derivatives evaluated at x is equal to a. For your approximating function, we have p of x is equal to c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a raised to 3 and so on. So, going back to our original function, we are trying to evaluate the value of this function, 1 over x. This will be f of x is equal to 1 over a. So if you evaluate this, p of a is equal to 1 over a, because this will become 0 up to the succeeding terms. What does that mean? Ibig sabihin, yung theory ng Taylor series is true because the approximating function is becoming equal to the original function, and that is 1 over